not recorded in speaker view, we cannot say it.
Recorded in speaker view, yeah.
Yeah. Okay, thanks.
Okay. Oh, Jasmine, you are in speaker view right now. Okay. So, so these are the plots for the first group. And let's see, the next one is find an equation for the line tangent to beta at t equal 1/4. So this is tangent line. So for the tangent line, I don't think I am being viewed here, even though we're in speaker view. Meredith is being viewed. You're being recorded too.
Could you pin yourself, pin your own video?
Can I do what now, Lauren?
Can you pin yourself? So put a pin. There's a button that says like pin me.
Yeah, let's see,
You
participants.
click the 3 dots on your own screen when you like move your mouse over your own screen and click the 3 dots. There should be an option.
Very good, Meredith. Thanks a lot. That might work. But we want the tangent line. And so for the tangent line, we'll need a point on, which is beta of 1/4. And we'll want the direction. You don't need the tangent direction, but the tangent direction is beta prime of 1/4. And then this is exactly what you need for a tangent line to a curve. And then whatever these turn out to be, then your tangent line is alpha of t equal beta of 1/4, the point on, plus t times the vector beta prime of 1/4. That's t times that. And t is any real number. So this is the equation of the tangent line. E, what is the temperature of the curve at t equal 1? Meredith, you let me know when you can't see the board. What is the temperature at t equal 1? So this is just simply taking the temperature function and plugging in the point beta of 1. So this handles the first group. Any questions on these first 5? Let's continue on through then. Compute the position, velocity, and speed of beta at t equal 1. So F, the position at beta equal 1 is beta of 1. The velocity is, we already found, is beta prime of 1. And the speed is the length of beta prime of 1. So these are the 3.
Yeah, and also
I asked for. Yes? Question?
yeah. She can't be mad at us, really.
Pardon me? I didn't hear who is questioning.
I don't think it was a question.
Okay. Some person's mother? All right. So is the temperature of the curve rising or falling at t equal 1? So what I would do is I would graph the temperature of beta of t. I would plot this. And this is what I asked you to do, I think, in one of the exams, I forget what. And the range of t's is 0 to 2. So here will be t, and here will be the temp of beta of t. And so when you plot that, you will get some curve. Not this curve, likely, but some curve. And at 1, the temperature is here. And the temperature is decreasing as you continue continue on the path. Now, this doesn't show the path. This just shows the temperature as you progress on the path. And at that point, it is decreasing. And it is decreasing because the derivative of the temperature of beta of t dt is less than 0. So it's got a negative derivative. So if you find this function and take the derivative, plug in 1, you will get a negative number. That's what this graph shows. Is the wind with you or against you at t equal 1? So I might point out that these two questions are about the integration. When you find like the average temperature, what you do is you integrate the temperature on beta and divide by how long beta is. But what you have here, what you are integrating is the temperature with beta of t plugged in. So when you're finding averages or that sort of thing with temperature, you are integrating the thing that I asked about in G. And now in the next one, when I ask you, is the wind with you or against you? When you have a line integral and you're integrating the integral of the force field, which is wind in this case, dot t over the curve, what you are integrating is the wind dot t. And what that is the following. If you take the wind, which is a vector quantity at this point, and you project it onto the tangent direction, then you get a certain length. And this length is positive. But if you would have, if the blue vector would have been out here, and you project it, then this length would have been a negative. So the wind is with you when this dot product is positive, and the wind is against you when this dot product is negative. This is a unit tangent here. So that's what I'm checking here. Do you know what we're doing when we're integrating? Do you know what kind of things we're adding up under the integral? And this one says, is the wind with you or against you at t equal 1? So you want to take the wind at beta of 1. This is a vector quantity. And you want to take the dot product with the unit tangent at beta of 1. And the unit tangent, you don't actually have to use the unit tangent, because the unit tangent is beta prime of 1 divided by the length of beta prime of 1. And you're just interested in positive or negative. This denominator is always positive. So if you take W of beta of 1, take the dot product with the derivative at 1, if this is positive, it means it's with you. If it's negative, then it's against you. Questions about this?
When doing the calculation, should you also take the integral, or is it okay if you just do the dot product?
The integral will not help you with this answer, because the integral kind of, sometimes it'll be against you, sometimes it'll be for you. Is this Lauren?
Yes.
Yeah, sometimes it's for you, sometimes it's against you, and the integral gives you the net. But what I was interested here is it just at one point, is it for you or against you? If the integral is positive, it means in general, it is in your favor. But at times during your trip, it might have been against you, just like real life, sort of. Does this answer your question, Lauren? Not really.
Yes, thank you.
Okay.
No, that clarifies it. Thank you.
So although these last two were pretty easy if you knew how to do it, they were conceptual. So these are kind of the theory behind it kind of questions, and I can test by just asking that simple thing. How much work is done against the wind or done with the wind when traveling along beta? So what I'm interested in now, how much work is done, that is the net. So the work is the integral of f dot t along beta. So this is what I wanted you to do, this line integral. Compute the average temperature of the curve. The average temperature is the integral of the temperature on beta divided by how long beta is. And then you have to know how to do these integrals. There's an expansion contraction factor for each one of these. And in this one, there is an expansion contraction factor, but it gets divided by the length of beta prime of t. So this is just w of beta of t dot beta prime of t dt, 0 to 2. And what is the moment of the curve in the x direction? I didn't ask you for the center of the curve, but I could have. The moment of the curve is you integrate x over this curve. Did I call the curve c or beta? Beta is the parameterization. I call the curve c. So this is the moment in, this is the integral you do. Rather than integrate one, you integrate x to get the moment in the x direction. Problem 1. This problem came right off a final from a few years ago, and people did pretty well. I mean, there were very few errors on problem 1, and the problems that caused the most trouble were the two that we talked about when you find whether or not the wind is with you or against you. When is that? H. Yeah, H and G. G and H caused the most problems. People didn't lose much, but they lost something. The computational ones went really well. So can you expect something like this? Yeah, I mean, it's multivariable calculus, so you're going to get all this stuff. I can ask this in different ways. Rather than ask you for the moment in the x direction, I could have asked you for the center, the geometric center of the curve, for example. But I asked a great deal of what I could ask about this particular question. I didn't ask Tn and B. I could have asked Tn and B. I guess I didn't ask those. But looking at a curve and picking out the geometric information and picking out the information as it pertains to a real valued function and a vector field, this is standard stuff. So it's on its way. You ready for number 2? Number 2. So number 2, this is in the plane now. The first one was in 3 space. This one's just in the plane. And so again, we have a vector field, F, capital F, I'll just call it little f. This is a vector field. And we again have a temperature function, a real valued function. So often I use wind as an example of vector field and temperature as an example of a real valued function, just to sort of pin those down. But this could just be any real valued function. This doesn't have to be the wind. It can be any vector field. You're given a region, R, and the region is bounded by 2 curves. y equals x squared minus 4x plus 4. Y equals minus x squared plus 8x minus 6. C is the boundary. So C is the boundary of R. This is the same symbol as you use for partial derivative. And that's it. Oh, no. CT is the top. So we have those things, and we're going to ask some questions about it. So first of all, plot the region R. Oh, and the vector field in a single plot. So plotting the region R, I would define the region R with implicit region. And you have to determine which of these is on top, and it ends up it's this one. So y is less than or equal to minus x squared plus 8x plus minus 6. And y is bigger than or equal to x squared minus 4x plus 4. And then x and y. And I would give this a name, R2 or D2. And then you would want to plot, or I think just region R2 will show it, or discretize. This should show it. And you should give this a name, plot R2. And then you want the vector field. This is a two-dimensional vector field. And you want the range of this vector field to be similar to the range of this so that it can be put together. So vector field equals, and then show the two of them together. Plots R2 VF. Now let's say you get these two plots and this one doesn't work out for some reason. Leave this command and just go on. You have limited time here. And so if you know how to do it, but Mathematica just isn't working for you, leave those commands there. If necessary, write me a little sentence or two of how you would do it and go on. Because I'm interested in if you know how to do it, not necessarily if you know how to use Mathematica. I would like you to use Mathematica, but if something screws up, don't let that mess you up. Graph the temperature function on R. So this is a plot 3D, not a parametric plot, not a vector plot, but just plain old plot 3D because you're plotting a function. Temperature function, and then x, y, z. This is temperature function of x and y, and x and y are in R2. It's plotting a function of two variables where the domain is R2. So this is B. C, create a contour plot. So this is plain old contour plot. Of the temperature function. And it's, I think, I forget the syntax. It might be the same. The syntax, I'm a little suspect, but it might be the same syntax. And it is contour plotting. And you can specify the number of contours if you want, or just let it pick for you. If you are not sure on what the syntax is, and this isn't in one of your templates, I have this stuff in my integration template. But if it isn't in there, use Mathematica Help to see what the syntax is. If you're still not sure, give me your best guess. If it doesn't work, I'll see that you knew the basics of it. You might lose a point, but you might not lose anything. Okay, next is F conservative. So this is just a check to see if you know how to check on conservative. And I'll probably ask you for a potential function, or I might. That would be next, so that you can see what it's good for. I forget what f of x and y is right now. 6xy minus 1. 3x squared plus 1. So you want to take the derivative of this with respect to x, with respect to y, in which case you get 6x. You want to take the derivative of q with respect to x, you get 6x. These are equal. Yes, it is. Oh, if so, find a potential function. So it is, so we'll look for a potential function. To find a potential function, you integrate this with respect to x. This is the way I do it. So you get 3x squared y minus x. And then I'll integrate the next one, q with respect to y. And we get 3x squared y plus y. But these can have constants with respect to the other variables. But now the potential function has a 3x squared y. It should show up, anything that shows up in either of them you need, but you only need one of these. It needs a minus x, it needs a plus y. That's it. So here is the potential function for it. And you can check it by taking the derivative with respect to x, in which case you get 6xy minus 1. And the derivative with respect to y, you get 3x squared plus 1. That's the vector field that we had. That's what it means to be a potential function. Find a parameterization of the top. If there are questions as we go, just speak right up. So this region looks something like this in the plot that you did in part A. And this is the function, this is the graph of the function y equals minus x squared plus 8x minus 6. And the bottom one is the graph of the function x squared minus 4x plus 4. And so the top, so this is CT. C is all the way around, but this is the top. So parameterization of the top, U of S, is using the graph parameterization, is S, the X value, and then the Y value is minus S squared plus 8S minus 6. But the important part is to figure out what this is. What are the limits of S? The graph parameterization is pretty easy here, but this part you need to do a little work. It is determined by the X values, or in this case, the S values, where these two graphs intersect. So to find those points, you set the two equations equal. Anytime you want to find intersection points, this is what you do. So we get 2x squared minus 12x plus 10 equals 0. 0 equals x squared minus 6x plus 5, x minus 5, x minus 1. So x is 1 and 5. So finding those points is important. And in the next problem, 3 dimensions, it's also important and a little harder to identify maybe, but here is this one. This is the parameterization. This is E. F, compute the average temperature over R. So the average temperature over R is this integral. Is this quotient of integrals. And you need a parameterization for R to do this. If you use the Mathematica parameterization, this is R, the R1 that I defined before. So this would be N integrate, or integrate will probably work. And you want to integrate the temperature function. And the temperature function of X and Y. And you want to do it for X and Y in R1. And this will be divided by sort of the same thing. So there is the average value, the average temperature over the region. G. So G is compute the work done by F along CT from left to right. So CT was the thing we just parameterized down there. And so this work is equal to the line integral of F dot T along CT. And now you can actually compute this. We have this parameterization of it. So this will be the integral of F. Oh, F was conservative, wasn't it? F was conservative. So if we find an antiderivative, and I think we did already, then you can take that antiderivative and plug in the 2 endpoints and subtract. So this is the antiderivative, this is the potential function. I guess, I don't know what to call this. Potential function P maybe. This isn't the other P, maybe I'll use the script P. This is the potential function. What do we get for that potential function? Does anybody have that? Just so anybody write down what we got for the potential function here? 3x squared y, I think, was part of it, right?
Yeah,
3x squared y minus x plus y.
Yeah, that's it. And so we need to take the 2 endpoints, the right endpoint and the left endpoint, and subtract. We already parameterized this, so I was about to do that, but it's easier to use this potential function. And the endpoints are u of, was it 1 to 5? And when we parameterized the
Yeah,
Yeah.
So this is u of 5, and this is u of 1. I miss the big classroom where I can just walk around and do these all the way around the classroom. but it is what it is. So this is the answer to this one. And it's because this is conservative that it made this easy. I think we'll have another one, or maybe earlier we did one where it wasn't conservative. On problem 1.
What is the importance that the work's being done from left to right versus right to left?
It will make a difference of a negative. This is the net force. The work in a way is the net force that's with you. If you get a positive going one direction, and it'll be the same value, but negative if you go the other way, Lauren.
So should we do, since it's left to right, the negative of it?
So if we went
Or
the left to right, will
is that counterclockwise?
this is not clockwise or counterclockwise. This is just along a curve. If we're doing Green's theorem, then the direction is important. Here, it's like when you integrate a function a to b, f of t dt. This is equal to f of b minus f of a.
Mhm.
Here you're going from a to b. So the final point is b and the initial point is a. And that's what's going on here. The final point is u of 5, because here is u of 1 right there, and here is u of 5 right here. So you begin here, this is like your a, this is like your b. You look at the antiderivative, that's this p, and you take p of this b minus p of this a, gives you the line integral. That's the fundamental theorem of line integrals.
Got it. I see why it's important then, left to right, to know which is the first and which is the second. Makes
Yep.
sense. Thank you.
It's always good to know what is the first and what is the second one. That's a general rule. It's always important. Unless the first will be last and the last will be first, then it's really complicated. So, all right. We good? We good?
Did we talk about computing the entire boundary?
I don't think we did yet, but
Okay.
here we're doing it the counterclockwise. That's H. Is this Meredith that asked me? Or
I was asking about I.
compute? We haven't gotten there yet.
Oh, I thought because I thought we were talking about one way or the other, and that's what H is.
No, we haven't. We just did H. We just finished H.
Yeah. And I was asking about I.
I'm wrong. We just did G. Now we're on H, and then we'll get I. So let's go them in order. So let me do
Okay.
H first. So compute the work done by F along the entire boundary. And this answer is 0. Why?
Because it's going around, right?
It's going around. Yeah, it's going around the entire boundary. And there's one other part that's important here to say it's 0.
Because it's conservative.
Exactly.
Oh,
It's a conservative vector field. If you make a loop with a conservative vector field, you begin and end at the same place. So it's like integrating a function from a to a. You get 0. F of b minus f of a. Well, f of b and f of a are the same. So if you subtract them, you get 0. But now, Meredith, I'm going to make sure that you can actually do some of these integrals. And so I've asked to find the whole length of this. And there are 2 parts. There's a top part, we'll find that length. There's a bottom part, we'll find that length. This is like Green Bay. And then we'll add those 2 together. So the total length equals length 1 plus, or length t plus length bottom. So the length of the top is the integral of the one function over the top curve. We've already parameterized that curve. And I think u of t was equal to t, and then it's the minus t squared plus 8t. I think I used s. Minus 6. 1 less than or equal to s less than or equal to 5. U prime of s is 1 minus 2s plus 8. So the speed, which is the expansion contraction factor in this case, is the square root of 1 squared plus minus 2s plus 8 squared. So this integral becomes the integral from 1 to 5 of the square root of 1 plus minus 2s plus 8 squared ds. So whatever that integral is, that's the integral, that's the length of the top. So the length of the bottom,
So we use 1 times the square root part.
Jasmine, what was that?
Should we use 1 times the whole square root part?
Yeah, but 1 times anything is that thing. So
Right. Okay.
I didn't write the 1 down again.
Okay. Thanks.
But if you put it down, it's okay. Let's see, what do we have next? The bottom. So we need to parameterize the bottom. Sort of the hard part we already did, defining the 1 and 5. So I'll call this v of t equals t, and then this is the bottom curve, which is x squared minus 4x, so it'd be t squared minus 4t plus 4. 1 less than or equal to t less than or equal to 1. V prime of t is 1 2t minus 4. So the length of the bottom is equal to the integral over the bottom of the one function, which is equal to the integral from 1 to 5 of 1 times the expansion contraction factor, 1 squared plus 2t minus 4 squared, and then this will be dt. So this is the answer to the length of the bottom, and the total length is a sum of those two. So what am I checking here? I'm checking that you actually can parameterize these two curves and that you can do the integrals, but I'm also checking to make sure that you know to do that you parameterize these separately and add up the results. Find the flux in the outward direction across the top boundary of the curve CT. So again, now we're using this top. U of s is equal to s minus s squared plus 8s minus 6 curve. And the integral of f dot the normal direction over CT is equal to the integral of f perp dot t over CT, and f perp of x and y is equal to f was 6xy minus 1, 3x squared plus 1. So it'll be 3x squared plus 1, and then minus, it'll be the negative of the other one. So 1 minus 6xy. So q minus p. And so we already computed u prime of s, 1 minus 2s plus 8. And now this integral is a dot product. So this is the integral 1 to 5 of f perp. 3x squared plus 1 is 3s squared plus 1. And then 1 minus 6s, and the y value is minus 8 minus 2s. Dot product with u prime. No. This is not right. It's s is for the x, but the y value is this. So minus 6s times the y value, minus s squared plus 8s plus minus 6. And then that's dot product with the derivative, 1 minus 2s plus 8.
Where did you get the f perp again? Did you take partial derivatives of f?
No. If f is equal to pq, then f perp is equal to q minus p. These two are perpendicular to one another. And this equality needs a little theory. And I did this in class. There's some work to be done here. To show this, but this is what it ends up to be, that f dot n is equal to, and this is our n from the Tn and b stuff, f dot n is equal to the line integral of f perp. So a long f perp. And so this isn't really a new integral, it's just the same integral, but of a different vector field. Meredith, we good here?
Yeah, thank you.
Yep. This is called a curl in 2 dimensions. Okay. I think we should go on to problem 3. We've spent a lot of time on problem 2, a lot of stuff to do, but problem 3 also has quite a bit of stuff, and we should take a look at it. In a way, a lot of this stuff is repetitive, asking you to do the same thing in different ways. But this one was the hardest problem. Here we have a vector field in 3 variables. Uh, 2xy minus 3 and x squared plus z and y plus 1. And R is the region bounded by these 2 curves. Z equals 3 minus x squared minus y squared plus 2y, and z equals 3. So let's just deal with this right away for a minute. S is going to be the surface of R. ST will be the top, SB will be the bottom, and so on. This also has a rim that I didn't ask about, but let's talk about this. So this is a paraboloid that opens down. You can graph it and see that. And z equals 3 is a straight line, is a plane. And so the region bounded will be that kind of upside down cup shape. And I wanted to talk about that a little bit because. So let's just see what the equation of this, let's see what this equation is right here of this curve. So we'd like to find the intersection of these two. So we set them equal. And if we do that, we get 3 minus x squared minus y squared plus 2y equals 3. So we get x squared minus 2y plus y squared equals 0. We need to know what shape that is. X squared minus 2y plus 1 plus y squared equals 1. Here I added and subtracted. I added 1 to both sides. So this is x minus 1 squared plus y squared equals 1. This is a circle of radius 1, but it's not centered at the origin. It's centered at the point in the xy plane, 1, 0. And its radius is 1. So this is the equation there. And this disk down here in the xy plane is the domain. It's the natural domain for this surface, the blue surface. And it supports this rim here, which is this curve around here, the bounding curve. And so this bounding curve, I'll call it C here, we can write this equation, alpha of t is equal to, alpha of t is equal to, and now the values that you want are here on. So I'm going to use cosine t, sine t, and it should be cosine t 1 plus cosine t and sine t, and the z value is 3, 0 less than or equal to t less than or equal to 2 pi. So this is a polar coordinates describing just this curve down here.
How did you go from x squared minus 2y plus 1 to x minus 1 squared?
This is a perfect square, x squared. Oh, this is 2x.
Okay.
Oh, I am sorry. I went the wrong way. I am sorry. Too fast, Lauren. We'll do this again. X squared plus y squared minus 2y equals 0. X squared plus y squared minus 2y plus 1 equals 1. So x squared plus y minus 1 squared equals 1. This is what I should have written. The 2y was next to the x squared, so I got carried away. So the center is 0, 1 in the xy plane, not 1, 0. And I'll use the polar coordinates type. So this time it is cosine t, and then 1 plus sine t, and then the height is 3. 0 less than or equal to t, less than or equal to 2 pi. So if you get this situation where you don't know how to deal with this domain in the xy plane, I give you an alternative, and that is that you can use a rectangular domain, and that rectangular domain happens to be contained in here, but use a rectangular domain rather than the problem that I gave you, and that makes it a lot that makes all the computations easier. And I think I took off 5 points if you use that version rather than this version. So if this is confusing, use the rectangular version. It's a lot easier. But if you can do this version, it's worth 5 points and makes you look good too. So let's plot the region. I'll plot this region right here, and we'll talk a little bit about plotting the rectangular region. So I would use an implicit region. And the implicit region makes this easy to describe because you want z less than or equal to 3 minus x squared minus y squared minus plus 2y. And you want z bigger than or equal to 3. So those two conditions by themselves describe this solid region up here, x, y, z. And we could call that R3. So this describes this region, allowing you to integrate over it, find the volume of it, and so on. But it doesn't allow you to, it's not enough to do the surface. There's a little bit more if you want to find the surface. Let me erase this picture, and then let's do some stuff with this. So plot the region. That should do that. Plot the vector field F. So this is vector plot 3D again. Part C is find a parameterization of the top. And that's what I did before. U of S and T, or I did the rim. U of S and T could be equal to S cosine T S times 1 plus sine T 1 plus S sine T.
How do you know when to parameterize it using S and T versus just S or T?
If it's two-dimensional, you need 2 parameters. If it's a curve, you need 1 parameter. If it's a surface, you need 2 parameters, S and T.
Okay, so then S would then be the radius, or in this
That's
situation?
the radius in this case, exact, or yeah, S stands for the radius.
How do we know that again?
That's just, I mean,
That's just what it is.
I set it up. This will be the radius. This is polar coordinates. I could have used R and T, but this is standard polar coordinate stuff. And the Z value is this, 3 minus X squared, R squared cosine squared T, minus Y squared, R squared sine squared T. These add up to minus R squared, plus 2Y. So that's plus 2 times 1 plus R sine T. So there is a parameterization for the top surface. R
How
will
could you
go from,
get 1 plus RST squares for in this one? R plus 1 plus R times sine T. Like, how could you get that?
wait a minute here. Oh, minus Y squared. Yeah, I needed, this is not quite right. Because it's this whole thing squared, minus the Y value, 1 plus R sine T, the quantity squared. and then plus 2y. So here is my x, here's my y, and I'm plugging in here to get the z.
When, because before you just said the z coordinate was 3. Why is the z coordinate now the equation?
What's this now?
Earlier you said it was cosine t, s sine t. That's the curve of the top.
No, that
Circle?
was the rim. That's just the rim.
Oh, okay. I
This,
thought you said that was the top.
no, and then I had a 3 here, you know?
Yeah, yeah.
That's just the rim. So if R is 0, you should get just that rim. No, if R is 1, we should just get the rim. 0 less than or equal to S less than or equal to 2 pi. 0 less than or equal to T less than or equal to 2 pi. So this was the hardest parameterization on the test. It caused some grief when I gave this on a final exam. This caused grief. If you do it the other way, which is using this rectangular coordinates, it simplifies all of this because it becomes much easier because you'll just get S between 1 and 3 and T between 0 and 2. So everything is simplified. It's the same idea, but the shape of the object determines how complicated it is. This one isn't overly complicated, but it, under the stress of the final exam, it gave grief. So, so if I give you an option like this, and you're having trouble doing this parameterization, use the rectangular one to sort of straighten things out. And then if you have time, go back and see how to do the other one. I'm gonna have to go. I got another one of these, but I did ask a divergence theorem question and a Stokes theorem question on here. I will want you to know some of these basic things like Green's theorem, Stokes theorem, divergence theorem, fundamental theorem of line integrals. Look at those. I've been known to ask those point blank. You know, what is the Green's theorem? Most of these things, there's a lot of repetition. Parameterize something, compute the volume, compute the measure, the length, the area, integrate a function, find the average, these sorts of things in all those contexts. And so this practice exam is a pretty good look at what we're going to do. I think the exam I give you will be doable pretty easily in an hour and a half. But it will take you, I mean, it will take some time. It just takes time to do some of this stuff. All right, I'm going to end our recording.